Hi everyone. Today we're going to be going through the solubility product constant. This is lesson 4.6, so it's going to be, unfortunately, a long video, I think. So buckle up. We're in for a long haul here. So solubility product constant is KSP. So we've had lots of Ks, right? We've had actually not too many yet. But in our next unit we'll have some more actually. But in this one we've had KEQ, we've had K in terms of our rate laws. Now we're talking about KSP. So the solubility product constant. This has to do with when ionic compounds dissolve. They break apart into their component ions. So this is dissociation. So you would have written in grade 11, you would have written dissociation equations, and we did touch on this again in our first unit here in grade 12. So if we look at silver bromide here, what this represents here is we've got a solution and we've got a little bit of solid silver bromide at the bottom of the beaker sitting there, but we also have some Ag plus in the solution and some Br minus in the solution. So we've got the ions, Ag plus and Br minus, floating around in there, but we've also got some solid AgBr. So this would be a system at equilibrium because we've got both parts in there. Now, if we were to find the KEQ for this reaction, we'd use the following equation. So if we have KEQ, we know that that's equal to products over reactants. So Ag plus multiplied by Br minus, and then that would be over the reactant, which is AgBr. However, hopefully you'll have noticed that this is a solid, which means we can't actually include it in that KEQ expression. So we're going to bring it up here because it's a constant, right? The concentration of that AgBr, because it's solid, it's not going to be changing. So we're going to end up with having KEQ multiplied by this. And then that's going to be equal to the two ions here. Now, this here combined, KEQ, multiplied by the solid concentration, or so the solid concentration of AgBr, that is going to be where we get our KSP from. Oh, I cut off there. Sorry. This is our KSP. So KSP is when we've got a solid in equilibrium with its ions there. And so KSP then is going to be equal to just the products. So the multiplication of the products here. So the solubility product, that's where we get the multiplication from here, constant here. Okay, so that's KSP. So looking at this one here, so what is the KSP of this particular formula here? So we've got calcium hydroxide, solid, is in equilibrium with Ca2+, so the calcium ion, as well as the 2 moles of the hydroxide ion, 2 OH minus. So KSP is going to be equal to, and then you just multiply the products. And we've got OH minus. Now you can't forget, you have to factor in that 2, and that's going to be squared there, okay? So what that means, so it's going to be calcium 2+ times OH minus concentration. So that's the KSP value, or the KSP expression for calcium hydroxide. Okay, now KSP values give us information. So if we have a very low value for KSP, that means the substance in question has a low solubility, because remember, KSP is just going to be equal to the products multiplied together, right? So if that number is small, that means that we don't have a lot of it that dissociated, right? So low solubility, not much dissolves. If KSP is very high, that would show us that that is this high solubility, because a whole lot of the solid ended up dissolving. So looking at this example here, which substance is the most soluble and which one is the least? The one that is the most soluble is going to be the biggest number. So that's going to be down here, our PbI2, and our least one will be the smallest number here, our copper 2 sulfide here. Okay, so KSP gives us information about the solubility. Now, this is sort of a shorthand here, just the types of solubility equilibria. We're going to be doing quite a bit of math. So Sorry, this can kind of shorten it up for us. So I'm using M and N. N is not nitrogen, okay? These are just variables, okay? So M and N as our positive and negative ion here. So basically the salt formation here, this is a 1-to-1 ratio. So we could have, we don't know what the charges are, but we would just know that they're in a 1-to-1 ratio, okay? So if we were to write our equilibrium equation, we would say Mn solid is in equilibrium with M plus N minus. Now, like I said, it's a 1-to-1 ratio, so this could also be M2 plus N2 minus. As long as those charges are the same, this will work. Now, if we were assigning variables to this, and we're going to be doing that right away here in the lesson, but if we're going to assign variables, this would mean that Mn is breaking apart into two concentrations. Now, the molar ratio between them is 1-to-1, so we would put an X for each of these here. So the solubility constant expression here, so this would be KSP, is going to be equal to M plus multiplied by N minus. And then in terms of X, what that means is KSP is going to be equal to X squared. Okay? Now, and then you could solve for that if that's what you were trying to do, which, like I said, we'll get to that here. Mn2, so if we had this situation, we've got Mn2 is in equilibrium with M2 positive, and this would be plus 2N minus. So looking at this, if we were to assign X's here, there'd be an X there, but this would be 2X because I'm following the mole ratio here. So KSP is equal to M2 plus times N minus squared. So if we were to put that in here, our KSP then is going to be equal to X multiplied by 2X squared. So if we clean that up, KSP is going to be equal to 4X cubed. Okay, so see, by doing this we can speed it up here. So M2N is our next one. If we have M2N breaking apart, we're going to be oops, I forgot a 2 there. 2M plus N2 minus. So KSP is going to be equal to, and here we've got, well, this is the same thing, isn't it? Sorry, 2N, wrong one. Hold on. There we go. Okay, so this one we're going to have, this is why I was all confused. So this would be 2M positive multiplied by N2 minus, and this one has to be squared here. So then our KSP using X's, we're going to have the same thing. We have 2 multiplied by X, so again we're going to have the 4X cubed here. And then we're just going to do 2 more here. But these ones are actually the same. So Mn3 and M3N. I'm going to leave this one because it's just the backwards of the top one here. So looking at this, I'm going to have I don't like that color. There we go. So Mn3 in equilibrium with M3 plus 3N minus, and so X and 3X, so your KSP is going to be equal to M3 positive times 3N minus, and that's going to be cubed. So now if we put the sub in the X for this, it's going to be X multiplied by 3X cubed. So if we work out the math on that, we end up with 27 times X to the 4th, okay? Because remember that cube applies to both expressions here, right? So 3 times 3 times 3 and X cubed. And we're going to get the same thing here, so you can add that in. You can figure out that there. Complete that one on your own. Okay, now that's just sort of showing you how the math works. We're going to use that now, excuse me, as we go through these examples here. So calculating ion concentrations or solubility from KSP. So we're first going to look at silver bromide here. So we've got silver. Now the KSP is temperature dependent. I should have said that before. Make sure you write that down. So your KSP will change depending upon the temperature, because we know that solubility is temperature dependent. So typically, right, as we increase the temperature, we increase kinetic energy, more particles are able to dissolve. Not true for all substances, but the vast majority of them. Okay, anyways, if the KSP for AgBr at 25 degrees Celsius is 7.7 times 10 to the negative 13, calculate the concentrations of Ag plus and Br minus. So first thing we're going to do, we're going to write our dissociation equation here. So AgBr solid is in equilibrium with Ag plus Br minus. Now it tells me what the concentration is, but let's let X equal the concentrations of silver plus and Br minus. And I know that they're both just X because it's a 1-to-1 ratio. When I'm looking at the forward reaction here, they're going to dissociate all in a 1-to-1 ratio here. So the KSP equation is going to be equal to Ag plus multiplied by Br minus. Now I've got the KSP, so I can just sub in my values here. So 7.7 times 10 to the negative 13 is equal to X times X, which is going to be X squared. So I can just take the square root then to solve for X, and I get an answer of 8.77 times 10 to the negative 7 molar. Well, actually, I sort of jumped a step. So that is what my X is equal to. So now I'm asking you to calculate those concentrations. So you would have to say then Ag plus is equal to Br minus, which is all equal to 8.77 times 10 to the 7 molar. Okay, so that's how you would do that problem there. So, yeah, so what that means is that's the maximum amount of Ag plus and Br minus that can be dissolved in this particular solution and have everything stay as it is. If you added more, you would see more precipitate out and it would change everything. So at this particular KSP, with this solubility, that's how much concentration of Ag plus and Br minus you can have. Okay, next one. What is the iodate ion concentration in a saturated solution of copper 2 iodate? So first step, we're going to write our equation here. So you probably don't know what iodate is. So it's Cu and then IO3 2 solid in equilibrium then with copper 2 plus, that's aqueous, plus, and then we've got 2 IO3 minus, and that's also aqueous. So that would be my dissociation equation here, and so here, this is where we get our X's. Again, I've got the KSP and S to find the concentrations, specifically the iodate ion. So I know that this is X, and this is 2X. So if we go through, we know that KSP is equal to copper 2 plus multiplied by IO3 minus, squared. So now we're just going to sub in our values here. So we've got 1.40 times 10 to the negative 7 is equal to X multiplied by 2X squared. And so this is going to be our 4x cubed situation here. Okay, so you have to divide by 4 there and then take the cubed root. So make sure you figure out how to use your calculator for that. Google it if you're unsure. So your X is going to be equal to 3.27 times 10 to the negative 3. But here's where you have to be careful though, because I asked you to find the iodate concentration, so that's actually 2x. So you have to go IO3 minus is equal to 2x, so that's going to be equal to 2 multiplied by this, which is equal to 6.54 times 10 to the negative 3 molar. And as per usual, you want to check for sig figs, right? So I've got 3 sig figs, so I'm good. All right, next. What is the Cr3 plus and OH minus concentrations in a saturated chromium hydroxide solution if the KSP is 6.7 times 10 to the negative 31? All right, let's write our dissociation equation. Okay, in equilibrium with chromium 3 plus aqueous plus 3 OH minus aqueous. So we're going to use X, 3X. KSP is going to be equal to Cr3 plus multiplied by OH minus cubed. Let's put our values in here. 6.7 times 10 to the negative 31 is going to be equal to X times 3X cubed. So this is where we get our 27X cubed, and that's 6.7 times 10 to the negative 31. So again, oh, sorry, that was x to the 4th. Oh my goodness. My apologies. 27x to the 4th. So again, you're going to divide by the coefficient there, the 27, and then you're going to take the 4th square root there. And you end up with an answer of, what did I say it was? That you get an answer of 1.26 times 10 to the negative 8. Now the question was asking you need to find, you need to find both concentrations. So you would state it, right? You'd say Cr3 plus then is equal to the 1.26 times 10 to the negative 8 molar. The concentration of the OH minus, you have to multiply that by 3, of course. And if you do that, you get an answer of 3.8 times 10 to the negative 8 molar. Okay, so that's where that came from there. Good. Now, we're just going to do the opposite here. So now we're calculating KSP from ion concentrations or solubility. So it's basically just the opposite of what we had been doing here. So the solubility of silver bromide is given as 8.8 times 10 to the negative 7 moles per liter. Determine the KSP. So if we have the solubility, that means we know the ion concentrations. Okay, that's what that is. So again, we're going to write our dissociation equation here. Ag plus Br minus. And now that 8.8 times 10 to the negative 7, that's the solubility. So that means that is what these concentrations are. So I've got a concentration of the silver plus as that, as well as the Br minus. So now I can literally just dump those values into my KSP equation here to find the answer. So 8.8 times 10 to the negative 7 multiplied by itself. And you get an answer of 7.7 times 10 to the negative 13. No units for KSP, okay? I did decimal there, sorry. No units for KSP, so you just leave it at that. Just make sure you have the right sig figs. Okay, if D plus concentration is 2.0 times 10 to the negative 5 at equilibrium, what is the KSP for D2A? So this is, of course, is a generic one, just using algebra here, or variables, I guess I should say. So looking at this, we've got D2A is solid. So for here, we're going to have 2D plus A2 minus. So looking at this, I know the concentration of this one. I don't know this, and I'm asked to find the KSP. Now, can I get that by looking at the molar ratio? Yeah, I can. So that's what we're going to do here. So you just have to multiply that by the molar ratio. So you're going to end up dividing by 2 for this. So this is going to end up being 1.00 times 10 to the negative 5 molar. Now, if you want to do that with dimensional analysis, you can. Just take the concentration and literally just multiply it by moles of A over D, and that's why I divided by 2 there. Whatever works for you. Okay, so now you've got these concentrations, so now you can just go ahead and find your KSP. Now, you still have to remember to square it though, so that's where some people will forget. A2 minus, so you're going to have 2.00 times 10 to the negative 5 squared multiplied by 1.00 times 10 to the negative 5. And then you end up with an answer of 4.00 times 10 to the negative 15. Again, no units on that one. Okay, last example. At 25 degrees, the solubility of Ag3PO4 is 1.8 times 10 to the negative 5 moles per liter. Calculate the KSP of this salt. So again, we are breaking this apart. 3Ag plus PO4, 3 minus. Now it tells me the solubility of Ag3PO4. So you're going to put that in now you have to factor in the mole ratio again. So again, what this means is you've got 1.8 times 10 to the negative 5. So now we just follow the mole ratio here. So I have to multiply this one for the silver by 3. So that's going to be 3 multiplied by the 1.8 times 10 to the negative 5. So that's where we would put our 3x in, right? That's where that 3 comes from. So now we can solve for KSP. KSP is going to be equal to the silver concentration cubed multiplied by PO4 3 minus. Okay, I'm just going to shortcut here, but just dump those numbers into that equation. So the 3 times the 1.8 times 10 to the negative 5, cube it, and then multiply it by the phosphate concentration again, and you end up with an answer of 2.8 times 10 to the negative 18. Okay, so these are all fairly similar. They're all just kind of worded a little differently. So you're just following mole ratios and really just doing this very mathematically. Approach it very mathematically. Okay, assignments. I Googled a calming picture for you all. I know it's a tough week for everybody. Assignment, I gave you some worksheets on KSP. The answer keys are all there, so take a look and see what you can do with it. Thanks, everyone.